Welcome along to your weekly SETI seminar series. Today we're fortunate to be joined by Heather Knutson. She's a Miller Fellow at University of California at Berkeley, and she got her Bachelor in Physics from Johns Hopkins University. And then she did a PhD at Harvard, where she was awarded a Harvard Merit Fellowship for outstanding performance over her 4 years at Harvard. And she graduated in January 2009. She's now working on the structure, composition, and atmospheric dynamics of planets outside our solar system, or exoplanets. And she's a high-precision time-domain infrared photometry and spectrometry expert, as we'll hear about today, I'm sure. She's a PI on many Spitzer awards, and since Cycle 4, and co-I on many ground-based telescope programs, including Keck and MMMT. Today she's going to discuss the dynamics of exoplanet atmospheres and what her group at Berkeley has been able to tell about these bodies. So if you'll join me in welcoming Heather.
All right, so first of all, thank you guys for inviting me here. It's a pleasure to visit now that I'm relatively local. So I would say it was an easy drive, but there was traffic, so not quite, but glad to be here. So today I'm going to tell you a little bit about some of the observations we're making to characterize the atmospheres of extrasolar planets. So my talk today is going to sort of fall into two halves. The first half, I'm going to tell you about some observations we've made to look at the atmospheres of a class of gas giant extrasolar planets known as hot Jupiters. So these planets are interesting because they have masses and compositions similar to that of Jupiter, but with one very important difference: they orbit very close to their parent stars. So these planets are much hotter than Jupiter, which has interesting consequences for their atmospheres. These planets, in fact, orbit so close to their host stars that we think they're probably tidally locked, or at least most of them are. So these planets would have then a permanent day side and a permanent night side, which again has interesting effects on the circulation. So I'll tell you about those planets in the first half of my talk. And then in the second half, I wanted to tell you about some new work we've been doing with some lower mass planets. I figured since I was coming here to SETI that you guys would be interested in hearing what's the smallest planets we've looked at and what can we learn about those planets. So I will tell you what these sort of cutting edge is in planet atmospheres for smaller and cooler planets. But first, start out with a little bit of background. So I know there are a number of summer interns in the audience, so I want to make sure that I fill in a little bit of background for exoplanets for those of you who might not be as familiar with the field. So there are two common techniques that we use to find and characterize extrasolar planets. These are probably the two most successful methods for finding planets so far. So the first is we can look at the Doppler wobble of the host star. So as the planet goes around the star, it tugs it back and forth in its orbit. We can see the Doppler shift of that star. And the amplitude of that Doppler shift tells us m sine I, where m is the mass of the planet and I is the inclination of the orbit. So remember, we don't know the orientation of the system we're looking at. Now, a small subset of these systems will line up perfectly such that we see the planet pass in front of the host star. And we can observe an event, an eclipse, if we're measuring the brightness of the star as a function of time. We see a small periodic dip in the star's light. So that periodic dip, if we measure the depth of the dip, it tells us the size of the planet relative to the size of the star, so we get the radius ratio. And in that case, now we know the orientation, so we know the inclination. So instead of getting m sine I from the Doppler measurement, we get the true mass of the planet. Now this is actually a really useful piece of information. So if we know the true mass and we know the radius of the planet, we can combine those two pieces of information and calculate an average density for the planet, which tells us sort of to a rough degree what kind of planet we're looking at. So this allows us to differentiate between large, puffy gas giant planets, similar to Jupiter, and smaller, rockier, much denser planets like the Earth. So we currently know of more than 400 extrasolar planets. I would have liked to actually bump up that number a little bit more. I think Kepler is really going to increase that in a couple of years. But for now, there's 400 confirmed planets, 400 plus. So this is just showing you the properties of those planets. Most of these planets were discovered with the radial velocity technique, although again, that's changing. So on the x-axis, I'm showing you the semi-major axis of the planet in AU. The y-axis shows you the mass of the planet, in this case, m sine I. So you can see that we know of planets out to sort of Jupiter's orbit and a bit beyond. That's just a time domain bias, so the fact that in order to know that what you're looking at is a planet, we want to watch it for one full orbit. So the surveys have only been going for about 15 years at this point, so that's about the longest orbit for any of the confirmed planets. On the y-axis, you can see that there are objects much more massive than Jupiter, but if I could zoom in on the lower corner here, the lowest mass planet that we currently know of that was discovered with radial velocity technique has an m sin I of about 2 Earth masses. So we're getting down almost to something the size of the Earth. So if I plot the transiting planets on this figure in red, you can see that there's an interesting selection effect. All of the known transiting planets pretty much are on this left-hand side of the plot. They all have very short semi-major axis. The reason for that is simply geometry. If we assume that the orbit is oriented randomly, the range of angles where you would see an eclipse from the Earth, if the planet's really far out from the star, there's a very small range of angles we're going to see an eclipse. If the planet's very close to the star, you can have a much wider range of angles, and you'll still see an eclipse. So we are biased towards finding short period eclipsing objects. So all of the planets I'm going to tell you about today generally have periods on the order of 2 or 3 days. So these are much shorter than anything comparable in the solar system. So just to put that in perspective. Okay, so let's focus in a little bit more on the transiting planets. So of the known and confirmed transiting planets to date, there are 74 of them. I checked this morning. I think that's the latest count. It changes all the time. So here I'm showing you the mass of the planet in Jupiter masses on the x-axis. So I'm showing you the radius of the planet in Jupiter radii on the y-axis. So you can see that a majority of the planets that we know of today that are transiting have masses and radii roughly similar to that of Jupiter. So these are all gas giant planets. If you look at exactly one Jupiter mass, and you look here, you can see that most of these planets, although they have the same mass as Jupiter, are a bit bigger. That's just a temperature effect because they're so close to the star, they're hotter, and so they're generally a bit puffier. Now, the most exciting part of this plot is actually these planets here on the lower left of the plot. So if we calculate average densities for these planets, they're higher than these gas giants. So these planets now we think have large solid cores, so a water, ice, or rock composition with a hydrogen-helium envelope on top. So these have masses and radii that are not that different than that of Neptune. But the very most exciting planets are these two down here. Both of these were announced within the past year. So these two planets are the first planets we would call super-Earths. So that's just defined as planets with masses below 10 times the mass of the Earth. So these are planets that are small enough that they may be mostly rocky in composition. So they may actually be getting into a regime where we would expect to find sort of a scaled-up Earth analog, potentially. It's not to say all of them will be like that. Some of them may also be scaled-down Neptunes. So one of the things I'm going to show you in my talk today is how we might distinguish between planet types for these low-mass planets. Okay, so there are 4 planets that you're going to hear a lot about today in my talk. 2 of those planets are these hot Jupiters that I mentioned earlier. So those planets are HD 209458 and HD 189733. So those 2 planets, 29458 is a little bit less massive, a little bit larger radius, a little bit hotter. It orbits a G star. So even though it orbits a little bit farther out, it still gets more flux. HD 189733, a little bit more massive, a little bit smaller radius, a little bit lower temperature. It orbits a K star. And it actually turns out to be a fairly spotty K star, which has been problematic for us. I'll tell you a little bit about that later on. And then these 2 planets over here are some of the lower mass planets that I showed you on the plot. GJ 436 is one of our Neptune-ish sized planets. So it is also, besides being smaller, it's also much cooler. And GJ 1214 is one of these 2 new transiting super-Earth systems. So this is pretty much one of the smallest planets that we know of right now, and also the coolest planet. So just sort of a side note, when I talk about these planets, I'm often going to mention something called equilibrium temperature. So all I mean by that is that we can estimate what we think the planet's atmosphere, or what we think the temperature of the planet's atmosphere should be. If we make a couple of basic assumptions, we know the incident flux the planet receives from its star, because we know its distance from the star. If we assume the planet has an albedo of 0, which we think is probably pretty accurate, at least for the hot Jupiters, so we assume it absorbs all of that incident flux, and then it re-radiates it as a black body in all directions, we can calculate what that black body temperature would be. So that's what I mean by equilibrium temperature. Okay, so one other important thing about these planets, the reason that I'm focusing on these 4, not a coincidence, these are actually 4 of the brightest transiting planet systems that we know of today. So these are really the planets where we have the best information, the most information, and the highest signal to noise for all of the measurements. And so as a result of this brightness, they're some of the best studied planets that we have. So I want to show you really like what's, given the most comprehensive information possible, what can we really say about these planet atmospheres? So if we want to study the atmospheres of these planets, let's go ahead and focus on those. So we can envision making a very simple list of some of the questions we might want to answer. So we might ask questions like, what's the planet's bulk composition? And so by that, I just mean this average density I talked about earlier. Is it mostly hydrogen and helium? Is it probably mostly rock or water? Sort of a very basic, rough classification. We can ask what its temperature is. I mentioned before we can predict what temperature we think it'll have, but that makes some assumptions about the atmosphere. We can actually go and measure the infrared flux emitted by the planet and determine its true temperature. Lastly, we can ask what's the composition of the atmosphere. Again, we can make an initial guess as to what we think the atmosphere might be, but how do we actually go out and test that initial guess? So I mentioned before, hot Jupiters are an interesting test case to look at. They're interesting for a couple of reasons. One, they're quite different than any of the planets we have in our solar system, so their temperatures are much hotter, so they may have different atmospheric chemistries as a consequence. In addition to that, we think they're tidally locked, so they may have a hot day side and a cold night side, very slowly rotating, interesting things for the circulation. But aside from being sort of a cool object to look at, we also like hot Jupiters for a second reason, and that's that they're good test cases for the techniques that I'm going to talk about. So these are really the biggest, brightest, hottest planets that we could look at. And so all of the techniques that I'm going to show you later are really easiest to do for these planets. And so then when I talk about how do we extend these to smaller and cooler planets, now we're talking about progressively harder and more harder measurements. So hot Jupiters, easy. We start with those first. We figure out what we're doing, and then we go to the small planets. I'm going to show you a couple of examples of small planets, but I think this is something that's really going to grow a lot in the next couple of years. There's a number of surveys which are going to significantly increase the number of low-mass planets that we have to study, low-mass transiting planets. OK, so how do we actually learn about the atmospheres of these planets? There's a couple of different techniques that we can use. One is we can watch as the planet passes in front of its star. Actually, first I should mention why bother with eclipsing systems to begin with. Many of these planets are very close to their host stars. They're also often quite far away. So these are really a lost case for imaging. You're never going to get an image of this planet separate from that of the star. And so the only way that we have to learn about their atmospheres is by looking instead of in the spatial domain, trying to resolve the 2 points of light, is to look instead in the time domain. We're looking for variations in this dot of light. So if we look when the planet passes in front of the star, I mentioned before that tells us the radius of the planet if we measure the depth of the transit, but it actually gives us more information than just that. If the planet is one of these hot Jupiters I was talking about, we know it has a large atmosphere. That atmosphere absorbs light at some wavelengths and not at others. So if we measure the wavelength dependence of the transit, so we measure the transit depth in a wavelength where the atmosphere is absorbing, we'll see a deeper transit. If we look at a wavelength where the atmosphere is transparent, we'll see a shallower transit. So that wavelength dependence of the transit depth tells us about the transmission spectrum of the planet's atmosphere. It tells us about its composition. If we wait approximately half an orbit, when the planet goes around behind its star, we see a second, much smaller eclipse. And in this case, if we look in infrared light, we can actually see the thermal radiation emitted by the planet disappear and then reappear as it goes behind the star and comes back out. So that actually tells us about the planet's day-side atmosphere. So here, the geometry of what we're looking at, you're seeing light transmitted through the day-night terminator. So remember before I mentioned we think some of these planets are probably tidally locked, so they could have a really hot day side and a cold night side. So in that case, what you're looking at here is sort of a transition region between those two hemispheres. Whereas here, during secondary eclipse, you're really seeing mainly the central region of the day side. So you're seeing the hottest part of the planet's atmosphere. So it may be that we see differences in the atmosphere between these two types of measurements, if the composition varies between the day side and the night side. So there's a third technique that we can use to study the atmospheres, and I'm not going to talk very much about this one today. So this is simply that if we want to learn about the circulation, we can measure changes in the brightness of the planet as a function of orbital phase. So if it has a hot day side and a cold night side, you can see that modulation as that day side comes into view and then disappears again. And the amplitude of that modulation tells you roughly the day-night temperature gradient. So just to mention that that's there. But for now, I'm going to start out by talking about transits. I'm going to show you what we can learn from those. So as I mentioned before, what we're measuring here is the wavelength dependence of the transit depth. So we're measuring the absorption of this annulus of atmosphere. And that tells us about the composition in that region. So here's an example of some of these observations in visible light. So these were taken with the Hubble telescope. This is with STIS. So this is now in visible light. It's approximately 300 out to 1,000 nanometers. So the color coding goes purple is the shortest wavelengths, out to red is the longest wavelengths. And so you can see that we can, so we're measuring here the wavelength dependence of the transit. I'll tell you more about this in just a sec. But first, a little bit of background. So this is actually, these slides I took out of my talk for a couple of years. And the reason I took them out is because we didn't have very much data. And it was really frustrating, actually. We had these initial measurements for a couple of planets that were pretty successful. And then what happened was the instruments that we were using on HST kept breaking. So these data right here were taken with STIS. STIS broke in 2004. So we switched to using ACS for our visible light spectroscopy. ACS broke a couple of years later. Then we said, all right, fine, we'll do it in the infrared. So switched to using NICMOS, and then NICMOS went down in 2008. So it's been a really frustrating period for us with these observations. Fortunately, it's the dawn of a new era. The servicing mission has repaired several of these instruments, so we're now back in business for these kinds of observations. So some of the stuff I'm going to show you is older, but let me just say that there's going to be a lot more coming in the next year or two now that we're able to make these kinds of observations again. So it's going to be really interesting now that we have a much larger set of planets to look at to see what the differences are between planets. OK, so one other thing I mentioned, so here I'm showing you the transit as a function of wavelength. So some of you may have noticed that the shape of the transit is actually different in different band passes. So here at short wavelengths, the transit is very sort of U-shaped. And up here at longer wavelengths, it starts to look boxier. The reason for that is that the star actually is not uniform in brightness. So the edges of the star are fainter, and the center of the star is brighter. That's something we call limb darkening. So as the planet passes across the star, it eclipses first this fainter part and then this brighter part. So the curvature of the transit is directly proportional to the amount of limb darkening. So limb darkening tends to disappear as you go to longer wavelengths. So what we really want is to measure the radius ratio of the planet to the stellar radii, or radius. We first need to understand how this limb darkening works as a function of wavelength. So we need to know something about the star in order to get to the quantity we ultimately care about, which is the planet radius. OK, so here are some actual data. So this is observations with ACS. So again, visible light, here 600 out to about 1,100 nanometers. So what I'm showing you here, the y-axis is the effective radius of the planet. And so on the bottom, have smaller planet radius. On the top, you have a larger planet radius. So that just corresponds to less absorption from the atmosphere, more absorption from the atmosphere. So absorption features on these plots go up instead of down, which is a little bit different for some of you. OK, so what I'm showing you here, the bottom in black is actually an atmosphere model for this planet. So this is predicting what we thought we would saw before we got these data. So here you can see we predicted there would be a large absorption feature from sodium and from potassium. And then as we move out into the near infrared, you start to see water absorption. So all I've done here is to take this model and integrate it over the band passes of our observation. So these blue points are just the model predictions in each of the band passes in which we observe. And so then in red up top is the actual data. So what we measured is that instead of seeing these big variations in the radius of the planet as a function of wavelength, we actually saw that it was basically flat. There may be some sort of gradually downward slope, but effectively all of these big features are not present in the data. So that was kind of a surprise. So the question is, what might be different about the atmosphere to give us this kind of sort of gradually varying signal? And the answer is that if you have a high altitude haze of particulates, that can give you sort of this wavelength independent. So it scatters light at all wavelengths equally. So that suggests that this planet has a haze of particles of unknown composition. So it's been suggested that it might be ENSTA-type particles or possibly a methane-derived soot. So if we look at the same planet now at longer wavelengths, so now this is a NICMOS observation in the near infrared. So now we're talking about 1.5 to 2.5 microns. It turns out we see the complete opposite. So in black is our model, in red is our data. And you can see that the model and the data both have these nice, large, big variations as a function of wavelength. So in this case, what you're seeing is water absorption. And then also the big surprise with these observations is actually methane absorption there at the longest wavelength. So this planet is warm enough, it's about 1,200 Kelvin, that we wouldn't have expected to see methane in its atmosphere. And that's something I'm going to come back to a little bit later. But at these temperatures, we would expect carbon monoxide to be the dominant carbon reservoir rather than methane. Methane you see mostly in slightly cooler atmospheres. So that's kind of an interesting thing to explain. All right, so that is one planet in transmission. So you can see already we have a lot to think about. We have a high altitude haze. That haze disappears at longer wavelengths. That allows us to set a limit on the particle size for the haze. They have to be micron or smaller particles. And we learned something about the composition. We see some water and some methane in the atmosphere. So what happens if we look at this same planet during secondary eclipse? So now we're looking in the infrared, and we're looking with the Spitzer space telescope instead of Hubble. So in this case, here are our secondary eclipse light curves. So the band passes of our observations go from 3.6 microns out to 24 microns. And you can see already by eye that the transit depth seems to get larger at longer wavelengths. So what this is telling us about is the flux emitted by the planet as a function of wavelength. So just to sort of put that another way, you're watching the planet disappear behind the star and then reappear. So what you see here is the flux from the star and the planet. The planet disappears, now it's flux from the star alone, planet comes back up. So that difference in flux tells you the flux from the planet as a function of wavelength. So if we want to compare these to models, how do we construct our models? So we need a couple of different things. We need a model for the star spectrum. So there, typically you use Phoenix or Cruz stellar atmosphere models. In this case, the star I mentioned is a K star, so about 5,200 Kelvin. And we also need a model for the planet atmosphere. So this is an example of a model by Barman et al. So this planet atmosphere model is approximately 1,200 Kelvin. And in this model, Travis makes a couple of assumptions about the planet atmosphere. So we need to know, first of all, what temperature it is. And the second thing we need to know is what the composition of the atmosphere is in order to predict the spectrum that we'll see. So in this case, what he's done is to assume a solar composition atmosphere. So he assumes the distribution of the elements in this planet's atmosphere is the same as in the sun's atmosphere. That's probably not ultimately going to be a very accurate guess. We know Jupiter has more heavy elements than the sun does, as do the other planets in our solar system. So this planet probably is enhanced by a bit, but that's a decent starting point. The other assumption that he's made is that the chemistry is in local thermal equilibrium. So that just means that the distribution of molecules, so how much water you have versus carbon monoxide versus methane, is determined by the local temperature and pressure in the atmosphere. And again, if you have photochemistry, if you have circulation, taking parcels of gas from the day side to the night side, you may alter this chemistry away from the equilibrium distribution. But this is sort of a place to start. So we take our two models, and we want to compare those then to our observations. So I mentioned before, here, out of eclipse, we're seeing the flux from the star and the planet together. Planet goes into eclipse, we see just the flux from the star. So the depth that we measure is then the ratio of those two. So the depth is just the planet flux divided by the sum of the planet and the star flux. And we approximate that as just the ratio of the planet flux to the star flux, because really the planets are always so much fainter than the star that we can neglect that term. So all I need to do to get my prediction for what we measure as a function of wavelength is to take the ratio of this spectrum divided by that spectrum. So now let me show you what that looks like. So here is wavelength on the x-axis, and now I'm showing you planet-star flux ratio on the y-axis. So this is now our observable. This is what we actually measure. This is the transit depth, or the eclipse depth, rather. So in black is the model. So you can see because the star is much hotter than the planet, when we ratio those two, we get something that goes up at longer wavelengths. And you can see also that there's features in this spectrum, and those features are mainly from water and a little bit of carbon monoxide in this case for this model. So what I've done here is to take the model, and in this case, the band passes that we're observing in are actually pretty big. So here, these dotted lines show you the Spitzer band passes for our observations. And so all I've done is taken this model and integrated it over each of the band passes to get a prediction for what we think we should see. So these black squares are the model predictions in each of the band passes. In blue is the actual data. So those are the secondary eclipse depths that we measure. So these were the 6 light curves I just showed you before. And you can see that actually, despite these assumptions that we made about the atmosphere being solar composition, local thermal equilibrium, that actually this model does surprisingly well. There's very few points that are that far off. Probably the worst offender is this point right there. The planet's brighter than we expected, but by and large, it's really not a terrible match. So that's the 6 data points we had 2 years ago. The question is now, with all of the observations that are available today, what can we really say about the planet's atmosphere? So here now is all of the data we have on during secondary eclipse for this planet. So in red were the points I just showed you before. These were the points we had a couple of years ago. There's now new data available. So this is taken with the IRS spectrograph on Spitzer, which unfortunately is now out of commission. I'll talk about that a little bit later. But, and there's also a little bit of HST data on this planet. So this is NICMOS data. in the near infrared. And so all I've done here is to take this part of the spectrum and put it in this panel here so you can zoom in a little bit and see what's going on. So if we take these data and we compare them to a model atmosphere for the planet, so this model is now from Knutson and Seeger. There's a couple different things that Knutson and Seeger have done with this model. One is now they allow the composition to vary. So instead of assuming a composition, we fit for it from the spectrum. And in this case, they only allow 4 things to vary. So the biggest signatures in the infrared for these planets we would expect are probably water, methane, carbon monoxide, and carbon dioxide. So those are the 4 things that they allowed to vary in their model. And then the other thing that they allowed to vary is the temperature as a function of height in the planet atmosphere. So this determines, for example, whether we see things in absorption or emission. And I'll talk about that a little bit later on. But so they fit for the pressure temperature profile and also for the relative abundances of these 4 elements. So here are the relative abundances that they get. So we can use these to test if our earlier assumption about the chemistry was accurate or not. There's already one surprise in these relative abundances, which is that the carbon dioxide abundance is much higher than we would have predicted based on the local thermal equilibrium. So this suggests that you have some sort of photochemistry producing excess carbon dioxide in this atmosphere. And it's in excess by, I think, something like a factor of 10 to the 3. So it's quite a bit extra. OK, so I mentioned before that we learned something about the composition by looking during transit. So I showed you a transmission spectrum, and I said we saw water and we saw methane. Now I've showed you a secondary eclipse and a day-side emission spectrum, and I gave you a list of elements and abundances. We can actually compare those 2 things and ask, is the composition at the day-night terminator the same as the composition in the center of the day side? So now we can test if the chemistry varies as a function of longitude on the planet. So here's the list that I just showed you in the previous slide. So here are the best fit relative abundances for the day-side emission spectrum. And you can see that things are roughly constrained to about an order of magnitude, plus or minus. So now we can compare those to what we got for the transmission spectrum. So in this case, because the wavelengths of the observations are much more limited, we can't really say anything about CO or CO2. But there is, we can make an estimate for the water abundance and for the methane abundance. So the water abundances, roughly the same, not too different. But the methane abundances are quite different, actually. So I mentioned before there's this strong methane absorption signal during transit. And we really don't see methane at all in the day-side emission spectrum. So this difference would seem to suggest that you don't really have methane on the day side, but you might have much more methane on the night side. That's kind of an interesting thing to try and think about, is how could you actually get that sort of, how could you cause that gradient to form, and how could you maintain that gradient given ongoing circulation between the day side and the night side? OK, so that is a lot of different observations for one planet. That planet may be typical of all of the hot Jupiters, or it may just be the oddball in the bunch. And the only way to know that is to look at other planets and make the same kinds of observations and see if we see the same features. So here now I'm showing you a second set of observations in secondary eclipse for the other hot Jupiter that I mentioned, HD 209458. So here I'm showing you a little bit earlier step in our analysis. So this is the raw photometry that we get out of Spitzer. So I want to talk a little bit about what we do to these data in order to make our measurements. So you can see at the 2 shortest wavelengths, 3.6 and 4.5 microns, that we see these big variations in flux as a function of time. Those big variations in flux come from the fact that the sensitivity of an individual pixel in our array is different at the center than it is at the edge. So during these observations, the star wandered by about 0.5 pixel within this little region. And as it wanders from the center towards the edge and back out again, we see these variations in the flux that we measure. And so it looks pretty nasty, but it turns out we can fix it relatively easily. So we fit this with the function of x and y position and divide it out. We get something that looks actually pretty good. So on the right, you see the normalized data after we remove our fit to x and y. And so you see the nice eclipses. At longer wavelengths, there's a different effect at work. We don't really see evidence for an intrapixel sensitivity variation. But what we do see is a gradually increasing ramp as a function of time. That ramp is steeper or shallower depending on how bright our object is. So bright things asymptote quickly, faint things have a much more gradual slope. So we think that that effect is due to charge trapping in the array. So you have these charge traps when you first start observing. So your photons hit the array, you generate electrons, but you don't read all of those electrons out. Some of them get stuck in the charge trap. But as time goes on, the charge trap gradually fills until eventually charge trap is full and you're getting 100% readout. So this is this asymptote to a constant value. It's So we fit that, in this case, with a function of log dt, which is just sort of an empirically a function that seems to work well in practice. And so we get, again, this eclipses on the right. So now if I take these 4 eclipse steps and I compare them to a model atmosphere for the planet, so now here I'm showing you again the same kind of plot I showed you before. So here's wavelength in microns on the x-axis, and we have planet-star flux ratio on the y-axis. So here in blue are our measured eclipse steps for this planet. And now I'm comparing these to the same kind of model atmosphere I showed you before. So this is a model atmosphere assuming solar composition, assuming local thermal equilibrium. And so I'm showing you one extra thing here. I'm showing you the pressure-temperature profile. So here's pressure on the x-axis, temperature on the y-axis. So in this case, what happens as you go higher up in the atmosphere, you see that the temperature decreases. So what we're seeing cooler, optically thin gas overlaying hotter, optically thick gas. And so that gives us features in absorption. So here you see mostly water absorption and a little bit of CO. So this model, unlike the last one I showed you, is a terrible match for the data. It severely underestimates the fluxes of the planet at these mid-infrared wavelengths. And so the question we can ask is, how can we change this model to provide a better match to the features that we see? So one way we might do that is if we could take these absorption features and switch them into emission features, we could make our model brighter in here. So how would we do that? Well, one common phenomenon in planetary atmospheres, we see many planets have stratospheres. So you have a point in the atmosphere where you have an absorber that traps incident flux from the star. It causes heating. And so instead of having this decreasing temperature gradient, you can have this hot layer higher up in the atmosphere. So we can do that with our model. We can add an extra absorber in, relatively low pressures. So now what we're doing is we're trapping some of that incident flux right there, and then we're also cooling the lower atmosphere below it. So now we have hot, optically thin gas overlaying cooler, optically thin gas. And that gives us features in emission instead of absorption. So this is this red model up top. You can see that it's not a perfect match for the data, but it's certainly much better. So that would suggest that this planet has some extra high-altitude absorber that causes it to form a temperature inversion and to have these features in emission. So it's not immediately obvious what the difference is between this planet and the last planet that I showed you. So what's different in this atmosphere that would cause this absorber to form and to be located where it is? They're basically the same temperature, a few hundred Kelvin different. They're basically the same composition. They're both gas giants, both in close in orbits to their stars. So the question is, what's the distinguishing characteristic that leads to the formation of these inversions? So what is the absorber and how does it come to be in the atmosphere at that spot? So when this planet was first published, we had 3 systems with observations. It's always easy to find a theory when you have three planets. So sure enough, started out with a theory, and that theory was you could have gas phase titanium oxide. So gas phase titanium oxide has a couple of useful properties. It is a very effective absorber in visible light, so that's where most of the star's flux is. And so if you want to trap a large fraction of the incident energy, you want to be a good absorber in visible light. It also has the handy property that it condenses out of atmospheres at cooler temperatures. So we would expect that these planets would be too cold to have gas phase titanium oxide. So that provides then a natural distinguishing characteristic between this planet. We say it's a bit hotter, so maybe this is in gas phase, and these guys, where it should have condensed out. So here, all I'm doing is showing you planets with a temperature inversion in red and without a temperature inversion in blue. So we had our theory. We had our 3 planets. So next thing to do is to test it with more planets. So 2008, 3 more planets are published. And our theory immediately has a problem. And that problem is XO1. So you can see here, this planet has basically the same amount of incident flux as 189733. And yet it has a temperature inversion, whereas this planet doesn't. So this planet can't have gas phase titanium oxide. It's just too cool. So that theory doesn't work for this planet. 2009, we have 3 more planets, actually 4. And so we have yet another exception to our theory. Here we have a planet that's hot enough, it should easily have gas phase titanium oxide, and yet it doesn't. So these 2 planets here are going to be a problem for this theory. So if this theory doesn't seem to be working, can we come up with an alternative theory? And indeed, there's an alternative theory to consider, which is that you might have sulfur compounds, which are good absorbers in sort of the shorter wavelength visible light. And so you get sulfur compounds when your chemistry is out of equilibrium. So you have a combination of advection of gas within the atmosphere and UV photons from the star. So those give you these extra sulfur compounds. And so this is Kevin Zonley's model. And so in that theory, planets with more sulfur compounds would have inversions. Planets with less sulfur compounds wouldn't have an inversion. And the tricky thing about that is that there's not a good observational marker that we can use to distinguish between the planets. It's not immediately clear which of these planets, if you had to predict, would have inversions and which wouldn't. So, so in the absence of a good testable prediction, being an observer, I said, all right, I'll just look for correlations. We don't really know what it is. We don't know what causes it. So we'll just see if we can come up with some thing that we can measure that predicts whether or not the planets have inversions. And so what things should we look at? Well, I mentioned before that this avenue of non-equilibrium chemistry seems to be promising. So maybe the UV flux is important. So rather than talking about the bolometric flux, maybe what we should really be concerned about is the UV flux received by the planet. So if we want to predict the UV fluxes for each of these planets, we need to know what kind of stars they orbit. So in particular, we want to know if the stars they orbit are active stars or quiet stars. So active stars, we know, have enhanced magnetic fields. They have more star spots. And there's also, they've been observed to have increased UV and X-ray fluxes. So we'd expect that for two stars of the same spectral type, one of which is more active, one of which is less active, the more active one is going to have a greater UV flux. So how do we actually measure activity in stars? Well, so coming to Berkeley, there happens to be a very wonderful database of high-resolution visible light spectra, which Jeff Marcy and his group have. And so those spectra give us a number of characteristics to look at for the star, but in particular, they allow us to look at calcium-2, H, and K lines, which are a well-known sort of historical metric for measuring the activity of stars. And so this is just showing you a sample of the spectra for different transiting planet host stars. And so these spectra are arranged in order from most active down to least active. And so you can see the most active stars have emission in the line core. That emission comes from, if in active stars you have non-radiative heating processes that heat the upper atmosphere, and so in the line core, which comes from higher up in the atmosphere, you get this emission. So more spots, more activity, more emission. And sort of the opposite, less spots, less activity, no emission at all. So we can measure the amount of emission, and that tells us roughly how active or quiet the star is. So here now is the plot of our measurements. So here I'm showing you stellar effective temperature on the x-axis, and I'm showing you what's called log r prime hk on the y-axis. So this is just, we measure the emission in the line core, and then we transform that into something that's relatively independent of spectral type. So this is the metric, this is the quantity that we talk about activity. So here now are all of the transiting planet stars we've looked at so far, for which we have both Spitzer data and these ground-based spectra. So again, I'm plotting planets without inversions in blue, planets with temperature inversions in red, and you can already see there's this interesting separation that starts to emerge, which is that planets without the inversions seem to orbit more active stars. And there's something that I'm ignoring here. I'm ignoring the distance between the planet and the star. So the amount of UV flux depends both on how much UV flux the star generates and also where the planet is. But the problem is it's not immediately clear how to take this quantity and translate that into an actual UV flux. And so that's what we're working on right now. But sort of to a reasonable sort of order of magnitude, most of these planets are in comparable orbits. And so this is sort of a good sort of initial look at which planets get more UV flux. So in this case, we see that planets without inversions have more UV flux. So the theory in that case is that these planets, that increasing the amount of UV flux is destroying whatever the absorber is that's responsible for the inversions. Okay, so if we want to test out this theory, aside from actually taking these numbers and translating them into UV fluxes at the surface of the planet, the other thing that we really want to do is we want to get more systems. This isn't a very statistically significant correlation. It's about 3 sigma, give or take. So what we really need is a sample of 20 or 30, 40 planets to which we can make these measurements and see if our theory holds up. So we need Spitzer measurements for a lot more planets. So fortunately, or unfortunately, depending on how you look at it. So Spitzer exhausted the last of its cryogen last summer. So for the first 5 years of the Spitzer mission, we could observe at wavelengths from 3.6 out to 24 microns. And here I'm just showing you the number of hours allocated to exoplanet observations in each of those years. So you can see that we sort of had an uptick at the end of last rally, but our numbers are relatively low until here. Spitzer runs out of cryogen. They start what's called the extended warm mission. So even though it's not cryogenically cooled, we can still observe at the two shortest wavelengths, 3.6 and 4.5 microns. And so during this 2-year warm mission, here now you can see there's actually a tremendous amount of time that's been set aside for exoplanet observations. And so what that big chunk of time buys us is it really allows us to do these big surveys of exoplanet atmospheres. So instead of talking about 1 or 2 or 3 objects and how they might differ, trying to understand what causes the differences, now we can really do statistically significant comparisons. We can have a large sample of planets. So that's really going to be a powerful tool for understanding what causes these inversions. So, but you might ask, there's a catch. There has to be a catch. And that catch is that we only observe at 2 wavelengths. So what do we really learn from those 2 wavelengths? So I mentioned before, here's our data for HD 29458. Here's our 2 models, one without a temperature inversion and one with a temperature inversion. So here, these are the 2 wavelengths that we have. And you can see it actually works out pretty well. So if you have an inversion or you don't have an inversion, it changes the slope between these 2 points pretty dramatically. And so based on those 2 points alone, we can make an initial guess. Assuming that we know the composition, assuming that we know the vertical thermal structure, we can make a guess as to whether or not it has an inversion. Now, fortunately, we're not limited to those 2 wavelengths. We also, in recent years, there have been a number of ground-based detections of secondary eclipses. This is a very exciting development. So for example, this is an observation of trace 3 in the K-short band, so it's about 2 microns by Bryce Kroll. And so by combining these ground-based secondary eclipse observations at shorter wavelengths with the Spitzer data, we can really get a good handle on what the atmosphere type is. So we can continue to expand our sample of planets and to look at the properties of their atmospheres and to compare them. OK, so I've talked a lot about hot Jupiters, but I promised I would tell you about lower mass planets. So in the later part of my talk, I want to just focus a little bit more on these 2 guys here. So GJ436, which is our Neptune mass planet, and GJ1214, which is actually approximately 6 Earth masses, give or take, so much smaller. One interesting thing I should mention about these planets, I said this guy orbits a G star, this one orbits a K star. These 2 planets actually orbit M stars, and that is not coincidence. So the reason that those 2 planets orbit M stars stems from the fact that if you want to look for really small planets, the easiest way to find those planets and to find planets that you can really follow up is to look for them around small stars. So just a comparison here, if you have an Earth-sized planet transiting a Sun-like star, you get a 0.008% eclipse. And if you have that same planet transiting now an M5 star, which is approximately 1/3 the radius of the Sun, that same planet creates a 0.1% eclipse. So for the same planet, you can make life much easier for yourself by looking around small stars. And especially if you want to do follow-up observations of the atmospheres, that's exactly what you need to do. OK, so there's one survey in particular that I should mention, the MERTH project, which is devoted exclusively to surveying nearby M-dwarf stars. It's looking at the closest 2,000 northern hemisphere stars. And so this survey was the survey that discovered this GJ1214, this lowest mass planet that I've been showing you. So this seems to be a good strategy. OK, I'm not going to talk too much about this, but we can just sort of say, these planets, I said, have higher densities, so we can talk a little bit about what the interior composition might be. So here I'm showing you different mass-radius relations, assuming different compositions. These are now planets with no atmospheres down here. So here, GJ436 is right here on the plot. So we have a pure hydrogen-helium planet up top. So this planet is smaller than you would expect if it was made just of hydrogen and helium. Here is a line for a pure water planet, and you can see the planet's a bit bigger than we would expect for water. So that tells us that the planet has a large solid interior with a hydrogen-helium envelope on top. So we're not quite down to true Earth analogs, planets with mostly rock and a very thin atmosphere. So this is kind of intermediate. So what predictions might we make for the atmosphere of GJ436? Well, I mentioned before, so we think it has a larger core. It might have a metal-rich or metal-enriched atmosphere. But the most important property is simply that it's cooler than the hot Jupiters that I mentioned before. So now at these temperatures, around 700 Kelvin, we would expect methane to dominate over carbon monoxide. And so that's a prediction that we can test. So here are some observations of GJ436 in secondary eclipse observed with Spitzer. So now we're going to take these measured secondary eclipse depths and compare them to the same kinds of models I showed you earlier, where we allow the relative amounts of methane, carbon monoxide, carbon dioxide, and water to vary. So here are the data with our models. And so in this case, there's actually something very surprising that came out of these data. And the surprising thing is that the prediction was that you should have 100 times more methane than you do carbon monoxide at these temperatures. And in fact, what was measured is that the methane was less than a part in 1,000 of the carbon monoxide. So this is a complete switch from what we would have expected. So this is kind of surprising. So that was a very interesting result, but it didn't stand for long before we had another result which seemed to contradict it. So a little bit of controversy here. So about a month ago, there was a paper that came out on AstroPH that looked at 6 transits of GJ436. So now we're doing transmission spectroscopy instead of looking in secondary eclipse. And so those 6 transits, there were 2 observations each at 3.6 microns, at 4.5 microns, and at 8 microns. So we can take those 3 measurements and we can get an idea of how the transit depth varies with wavelength. So when the authors of this study published their paper, they only included 4 of these transits in their analysis. So if we were to look at this and say, all right, gosh, if there's any transits that we really want to throw out, we don't really trust, which ones don't we like? So I would suggest maybe these 2 kind of look a little bit, yeah, there's some correlated noise. So here on the bottom, I'm showing the residuals from the best fit solution. So these have much more noise in the residuals than these guys. So these sort of seem suspicious to me. I would say I wouldn't necessarily trust the transit depths from these. But what these authors did is they agreed with me at 4.5 microns. They said, all right, we'll throw out this bottom transit. We'll keep the top one. But they did the opposite here. They kept this transit down here, and they threw out that one, which would be fine if the radius we measure is the same in both observations. Turns out it isn't. So here is their measurement. So there's their transit depth at 3.6, transit depth at 4.5, transit depth at 8. And so what they say is that they see this strong wavelength dependence of the transit depth. So they see here deeper transit, here shallower transit, here deeper. And this particular signal really is only possible to fit with a lot of methane. So that, at first, seems to contradict what we saw earlier, that carbon monoxide was far more abundant than methane. But let's take a step back for a minute and say, well, what if we kept those transits? Or what if we had made different choices about which ones we kept or which ones we threw out? So here now are all 6 transit depths. And you can see that this signal that they see depends a lot on which ones you pick. So if you pick that one there, and that one there, you can kind of get the same thing as them. Whereas if you pick that one there and that one there, you can get the complete opposite. So what's going on? So I mentioned before, there were a couple of transits that seemed more suspicious. So those 2 right there were the ones that I marked out as having more correlated noise. They seem to be a little bit less reliable. And so if we throw out those 2, then you see something that's basically consistent as a function of wavelength. There's some possibly absorption signal there, but really nothing that's going to be terribly statistically significant, and certainly not a whopping amount of methane. So we can ask, well, if you take these new points, what kind of model can you fit those with, and does it match the Dayside model? So here in brown is just the same model I showed you on the previous plot. So this is now roughly the same composition, but the model was generated by Nikum and Husadin instead of the authors of the other paper. So now for comparison, here are 3 band passes. Here are 6 transit depths. There are 2 suspicious ones. And so now if we throw those 2 out, we can ask what new composition can we fit the remaining points with? And what does that look like? So that in green is now a new model for the planet where we have very little methane, a lot of carbon monoxide, and some water. And that model matches those points much better. So I think we haven't yet reached a final answer with these data. It would be nice to get consistent answers for all of our observations, so we're working on these points here. But I think the answer is to be careful of what you keep and what you throw out before you rush to conclusions. So, right, so that's it for GJ436. And then I'm almost out of time, but I wanted to say something very briefly about our smallest transiting planet, which is very exciting, GJ1214. So this planet is around a very low mass star. So here I'm plotting the planet and the star to scale. So GJ1214, 6 Earth masses, about 3 Earth radii, and the star is about 16th the mass, 0.16 the mass of the sun. So if I calculate the transit depth for this planet around the star, it's actually about 1.5%, which is an interesting number because 1.5% is the same as the transit depth for HD 29458, which is one of our well-studied hot Jupiters that everyone's looked at, and it's relatively easy to measure. So this planet, all of the signals we would want to look at for this planet aren't that different than the hot Jupiters that we were looking at before. So this is a really good system to make these kinds of observations. So if we look at this planet, the average density is about 1,900 kilograms per cubic meter. So that tells us that it can't be pure rock. It might be water with a steam atmosphere, or it might have a larger rock composition with a little bit of hydrogen and helium on top. So there's some question of what kind of atmosphere it might have. So the question is, can we tell the difference? Can we see if it actually is a hydrogen-dominated atmosphere? Can we tell if it's a water vapor or steam atmosphere by looking during transit? So there are some nice model predictions for this planet from Milleriki and Fortney. So this now shows the predicted transit depth as a function of wavelength. So again, absorption features are up here. So you see absorption from water, a little bit of carbon dioxide, a little bit of ammonia, maybe some CO2. So the top 3 models here are all hydrogen-dominated atmospheres, and the lower 3 models are a steam atmosphere, half water, half carbon dioxide, or sort of a Venus-like atmosphere. And you can see the features for those atmospheres are much, much smaller. So the question is, why do we see this big difference? And that's just a very simple relationship. We can estimate the amount of absorption that we get is just proportional to the diameter of this annulus. So if we have a puffier atmosphere, the annulus is larger, and we see more absorption. If we have a more compact atmosphere, the annulus is smaller, we see less absorption. So we can predict the scale height of the atmosphere with a very simple equation. H is just kT over g mu. Mu is the mean molecular weight of the atmosphere. T is the temperature. K and G are so gravity and then just a constant. So for this planet, if we vary the mean molecular weight of the atmosphere, these atmospheres are much, much heavier than these. These are mostly hydrogen and helium. So this number for those atmospheres is small. So we see puffy atmosphere, lots of absorption, higher mean molecular weight, smaller atmosphere, less absorption. And so we can, on a very rough level, even without worrying at all about what the specific features we see are, we just measure the average size of these features, we can tell the difference between hydrogen-dominated and heavier atmospheres. And so this big signal actually would be detectable with HST. So there are observations planned for this fall to look at exactly that. OK, so I'm not really going to say that much. I had hoped to have a little bit of time to talk about true Earth analogs. But just to say that they're a little bit smaller than this planet that I was telling you about, GJ1214, not terribly small. But this is really sort of a best case scenario. This orbits a really small star, really nearby, bright star. In order to find Earth-like transiting planets, I think I don't need to tell you guys here in this room that Kepler is going to find an amazing number of new low-mass planets and also things with longer orbital periods. And so that's going to be a really neat set of systems to study. But the catch to that is that most of those systems are going to be around larger stars, sort of sun-like stars, rather than these M dwarfs. And most of those planets are going to be around fainter stars. So most of the Kepler planets are going to be really hard to do these kinds of observations for. But we might get lucky and find a few more transiting M dwarfs. And if we do find an Earth around an M dwarf, we probably couldn't do much with it with Spitzer. But JWST is going to be launched in just a couple of years, we hope. And so it has a much larger mirror. So Spitzer is 0.85 meters, JWST is 6.5 meters. So we can make the same kinds of measurements. JWST works in the same wavelengths as Spitzer, but much more effectively. And so JWST probably actually could make these measurements for a true Earth-sized planet, with the caveat that it needs to be around a nearby star and it needs to be a low-mass star. So with that, I'm just going to finish up by saying I've told you a little bit about hot Jupiters. And the big question right now is we're trying to understand why we see different types of atmospheres for those hot Jupiters. I told you a little bit about what we're starting to do with smaller and cooler planets. And we're seeing already some very interesting things. And then in the near future, we would like to be able to extend these observations to planets that are really sort of Earth analogs, if we can find them. So with that, take questions.
Heather, is there anything that you can do with Herschel at all?
So the trouble, yeah, I'd like to do something with Herschel. What we found with Spitzer is that there's only a few systems where we can detect a secondary eclipse in the MIPS bandpass, so at 24 microns. And the reason for that is that the star, you're sort of moving off the tail of the star's flux. The star gets fainter, the zodiacal background increases, and so the noise in your light curve goes up as you go to longer wavelengths. So we could maybe do something with the very shortest wavelengths on Herschel, but things out at like 30 microns are really not, unfortunately, useful to us.
Given expected stellar variability in the UV, would you think that some of these atmospheres would change temporally in a way that you could observe and correlate with H and K activity?
Yeah, that would be a cool experiment to do, actually. Yeah, so for example, the sun's flux in Lyman alpha varies by a factor of 2 between the solar minimum and the solar maximum. So even relatively quiet stars do show a lot of variability in the UV. Yeah, the trick would be getting simultaneous observations that span enough time and with enough precision to see that variability. I think we're still debating right now whether or not there is variability in these atmospheres, and if so, how often and what time scales and what kind of variability. So yeah, before you worry about what it correlates with, you have to show that it's there to begin with. And I think that's the point we're at right now, is proving that it's real variation and not just, poorly removed instrument effects, for example.
Well, first of all, I'd like to thank you for a wonderful talk, very insightful. I wanted to ask you, what is your insight into standardizing the Spitzer observations? In other words, 2 or 3 different teams analyzing the same data sets. And this was not just the case of what you showed there. There's other planets, some of the ones that we observe. Sometimes teams analyzing the same data set, they can be off by 2, 3, 4 sigma in those depths, either of the transits or the secondary eclipses. What's your insight in how that could be improved and what remains to be done?
Yeah, so I think that we are working towards sort of an idea of best practices for dealing with Spitzer data. So there are certain things that seem to work better than others. So for example, getting the position of the star with a Gaussian fit instead of doing the flux-weighted centroiding, which many of us used for a long time, I think gives better results. It helps to have different teams analyze the same data sets so that when we compare and get different answers, we can understand why we differ. So I think that's a healthy thing, actually, to have competing analysis. But yeah, so far it's just been a lot of talking back and forth to try and understand whenever there's differences in how we do the analysis to try and figure out what's best. The frustrating thing is that it seems like what's best may vary from one observation to the next, depending on if you're near the edge of a pixel or the center of a pixel, depending on if it's a bright star or a faint star. And so sort of mapping out best practices for those as a function of those other variables is turning out to be a little bit more complicated than we'd hoped.
Thanks.
Could you talk a little bit more about why doing these kind of characterization observations is harder with Kepler targets and so forth? Like what precise characteristics are necessary to achieve these observations?
Sorry, say that again?
What qualities should a translating system have in order to be a good candidate for these kind of observations?
So all of the signals that you see are ratioed to the star's signal. So when you look in secondary eclipse, the size of the signal that you see goes as the radius ratio and also the ratio of the temperatures if you're on the Rayleigh-Jeans tail. So by having smaller stars and cooler stars, you make the size of the signal larger. And if you have also a brighter star, so if you have a nearby star, then you give yourself more photons, so your relative precision improves. So you want small, cool, nearby stars, ideally. But then those are also spotty and variable, so you can't really win everything.
So you mentioned that with JWST, you may be able to characterize Earth twins, given a favorable enough, Earth twin around, if there's one around very nearby M dwarf, for example. Mm-hmm. So what are the chances of a target like that actually existing and being detected by Kepler, let's say, and so you can then go ahead and follow it up? And also, what kind of characterizations would you be able to do, for example, JWST on it? For example, can you detect Earth levels of oxygen and water and so on?
Right. So let me answer your second question first and then sort of back out of it. So what kinds of observations could we do for Earth analogs? Most of the work would probably be transmission spectroscopy instead of secondary eclipse. And the reason for that is those planets are much cooler. So now you have to move to longer wavelengths in order to get any of the black body flux from the planet. And so it gets harder always when you go out to 20 microns instead of 5 microns that we've been working at with hot Jupiters. So I think most of what you're going to see is transmission spectra. And what you're going to learn from those is going to be sort of a very rough ballpark, what's the atmospheric composition. So we're talking about things like water, methane, CO. Could you detect ozone? Yeah, I've seen arguments both ways, and I think that's really kind of marginal. So mostly whatever the most common constituents and spectroscopically active constituents of the atmosphere are. You could sort of talk about those. What are the prospects for finding a system like that? I think probably the odds of Kepler finding a system like that are low, just because Kepler's field of view is limited to 100 square degrees on the sky. And so the number of nearby bright M dwarfs in that field of view is not very many. So if those M dwarfs have planets, surely Kepler will find them. But if you really want to increase your odds, you really just need to do an all-sky survey of all of the brightest M dwarfs. And so this is the approach that this MERTH survey has taken. You probably would want to improve a bit on that. MERTH isn't really sensitive to Earth-sized objects. It's sensitive to things down to a few Earth radii, but not much smaller. So you would need to do a MERTH-like survey, but with better precision if you wanted to go after the Earths. And the odds of having a transiting Earth depends on how common Earth-like planets are around M dwarfs. We don't really know the answer to that question. The thing that helps you is that if you want something that's Earth temperature, it's much closer to an M dwarf than it is in the sun. So in the sun, you're looking for something that's transiting at 1 AU, which is statistically not very likely. With an M dwarf, you're looking for something that's transiting at like 1/10 of an AU. So at least the geometry helps you a little bit, but how many planets like that are out there, I don't know.
Well, would you care to throw out an estimate when you fold in all the probabilities, of say detecting water and oxygen with transits in the next decade?
I bet we will only have a couple of systems that really fit that description. I'd be really surprised if there was more than 10, even if you assume every planet, every M dwarf has multiple planets. Just the odds of it being transiting are not great. But I'm sure for those planets that we do find that are favorable, that JWST will, if we can convince the TAC, devote quite a bit of time to the most exciting one or two of those systems, and we'll be able to get sort of a rough idea of what the atmospheric composition is.
So the Miller-Rickey and Fortney results seem to imply that you're kind of out of luck with primary transits for measuring sort of super-Earth carbon and water-rich atmospheres because of the small scale height.
Mm-hmm.
Is that true in general? And if so, what about the secondary transits? Are they, is that something we might be able to see these type early terrestrial planet atmospheres with?
Yeah, so, right. So you could maybe with JWST, and so here I said we can't detect the smaller signal with Hubble, but maybe with JWST we could. So maybe we could do a bit better. Still kind of tough. If you have a slightly larger or slightly warmer planet, there's sort of a crossover point where it becomes easier to look in secondary eclipse than it does in primary eclipse, depending on what the scale height of the atmosphere is. So I think the answer is the best kind of measurement is going to depend on the system. Some will only get secondary eclipse, some will only get transmission. Some of those will only really have an upper limit in transmission, which we could then at least use to rule out the hydrogen-dominated atmosphere. So it's going to be bits and pieces.
Right, but you're not giving up on it. It's not impossible.
No. I think the hope is that we have many, many transiting planet systems to choose from, because then you can really choose the best ones that give you the best signals and then actually go out and study those. So we benefit tremendously by having these ongoing surveys like Kepler and like MERTH, and being able to choose the very best targets rather than getting stuck with, if you only know about one transiting planet system, that's all you can observe, and it is what it is.
What happens if your planet has an orbiting satellite that is relatively large?
Yes, you could see that. So there's a couple different ways you could see that. You might actually see transits of the object. So it would alter the transit light curve if the moon was sort of trailing or leading the planet when it ran across the star. So maybe you could see that actual change in the light curve. The other thing that you would see, though, is that you would see variations in the time of transit for your bigger planet, because the moon and it are orbiting around a common center of mass. So it's going to deviate from what you would expect if it was just by itself in a circular orbit. So timing variations, I bet, would be one of the first ways that we would detect a satellite around a planet.
Pardon the trivial question, but our atmosphere is mostly nitrogen. Why not a nitrogen atmosphere
Oh, in the models?
in your observations and your plans, your models?
That's a good question. So Eliza Miller-Rickey is at Santa Cruz, so she's close enough that you could possibly ask that question yourself. I'm not sure why she didn't try nitrogen for this one, except that the planet is large enough that it's quite different than the Earth. So maybe it's a little bit difficult to predict what kinds of atmospheres you might see for these sort of 1 to 10 Earth mass planets, because there's a range of different formation scenarios that you can envision that would give you planets in that mass range. So certainly she could try a nitrogen atmosphere, and it would be interesting to see what that looked like. My bet is it would be pretty similar to the other sort of heavier atmospheres.
Also, nitrogen is spectroscopically inactive and only shows up in most cases through pressure broadening of the other lines.
Yeah, so you'd probably see mostly water features in that atmosphere. But if you're asking, we can actually calculate what the scale height would be for an Earth-like atmosphere if we wanted to easily with that formula.
It's just that it's hot.
Yeah.
The atmosphere is very hot. So on Earth, CO2 is condensed as carbonate rock, and water is condensed as oceans. On this planet, it's much too hot for that. So water and CO2 are much more abundant than nitrogen, and so that's a very rational first start.
Well, there you go. Even better answer.
Okay, well, if there's no further questions or comments, then will you join me in thanking Heather for her great talk?